Welcome, AI architects! Get ready to unlock the true cognitive power of cloud AI by mastering the core elements of prompt engineering. Welcome back to the training series. Today, we are focusing on formulating instructions for cloud AI, specifically diving into the core elements of an effective request. In the world of generative AI, having access to massive, multi-billion parameter foundation models on Amazon Bedrock is incredibly powerful. However, these models are essentially cognitive engines waiting for direction. If you provide a weak, ambiguous prompt, you will receive a generic, unhelpful response. The magic lies entirely in prompt engineering. Prompt engineering is the strategic practice of crafting and structuring inputs to guide large language models toward generating highly accurate, relevant, and specialized outputs. It is the crucial bridge between human intent and machine execution. Without prompt engineering, users suffer through trial and error, encountering hallucinations and irrelevant data. By mastering prompt elements, we achieve higher accuracy, greater flexibility, and vastly improved user experiences. To objectively measure our success, we use the RACA framework: relevance, accuracy, completeness, clarity, coherence, and appropriateness. If your prompt generates a response that passes the RACA test, you have engineered a phenomenal request. So, what exactly goes into building a production-grade prompt? It is not just typing a question. A robust prompt is a carefully assembled architecture containing distinct components: instructions, context, roles, input data, negative prompts, and output indicators. Let us explore these core elements. This flowchart illustrates the translation of thought to action. Raw human intent is structured via prompt engineering, transmitted to the Bedrock LLM, and produces an output that must withstand rigorous RACA evaluation.
The very first core element of any effective request is the instruction. This seems obvious, but it is where most developers fail. An instruction is the explicit task description. It tells the foundation model exactly what cognitive action to perform. Are you summarizing, translating, writing SQL code? You must state the verb clearly. Why do broad instructions fail? If you say, discuss the global economy, the model has no boundary. It might give you a one-sentence quip or a 10-page dissertation. Very fast. Instead, your instruction must be highly specific. Summarize the key factors affecting global economic growth in 2025 in exactly 3 bullet points. Precision completely eliminates ambiguity. The next crucial element is the output indicator. This tells the model the exact structural layout you expect. Do you need a JSON payload, a Markdown table, a Python script? By specifying an output indicator, such as instructing the model to generate a table with headers or telling it to output raw SQL, you prepare the response to be seamlessly parsed by your downstream application. Furthermore, you should include directives like skip the preamble or do not include conversational filler. This prevents the model from generating annoying text like, here is the SQL query you requested, ensuring you get pure, clean data back from Amazon Bedrock. Observe the difference. A vague request introduces massive ambiguity, resulting in chaotic, unpredictable output. A precise instruction combined with strict output indicators mathematically guarantees highly structured, application-parsable data.
Instructions tell the model what to do, but without the right context, the model might not know how to do it accurately. What is context in prompt engineering? Context is the relevant background information, domain-specific knowledge, or temporal data that you inject directly into the prompt to ground the model's response. Remember, foundation models are frozen in time based on their training data. If you ask a model about a highly specific, proprietary internal company document, it will hallucinate because it has never seen it. To solve this, you must provide the text of that document as input data alongside your context. For example, you might say, based strictly on the following Q3 financial report snippet, summarize our profit margins.
You then paste the snippet into the prompt. Amazed! This grounds the model. It forces the generative AI to abandon its generalized knowledge and focus strictly on the secure proprietary data you provided. This exact principle, injecting external data into the prompt context, is the absolute foundational architecture of retrieval augmented generation, or RAG. By supplying rich context and clear input data, you transform a generic LLM into a highly specialized domain expert. This illustrates the grounding process. We inject proprietary input data alongside explicit instructions to formulate a rich prompt context. This completely overrides the model's generalized knowledge, forcing a strictly grounded, factual output.
Now we introduce one of the most transformative elements of an effective request: assigning roles and personas. When interacting with advanced models like Anthropic Claude 3 or Meta Llama on Amazon Bedrock, you are not just querying a database. You are interacting with a cognitive engine capable of assuming complex identities. Why is this useful? By assigning a persona, you instantly calibrate the model's vocabulary, tone, and level of expertise. If you ask a model to explain quantum computing, it might give you a dense, PhD-level mathematical response. But if your prompt starts with, "You are an enthusiastic kindergarten teacher, explain quantum computing in simple, fun terms," the output changes radically. The model restricts its vocabulary, uses analogies, and adopts an encouraging tone. In enterprise applications, we frequently use system prompts to establish these roles globally. A system prompt sits above the user's query and dictates the absolute laws of behavior. For example, a system prompt might be, "You are a senior financial auditor for an enterprise bank. You must communicate with extreme professionalism. If you do not know a financial fact, you must state, 'I do not know.'" Establishing a persona ensures that your generative AI application maintains absolute brand consistency and expert-level alignment across thousands of interactions. Notice how the persona alters the logic. The system prompt establishes a robust vocabulary and tone filter. When the user query arrives, it passes through this cognitive filter, resulting in a strictly role-aligned expert response. As your prompts become more complex, combining instructions, context, input data, and examples, they can turn into a massive wall of text. If a human struggles to read an unformatted block of text, an LLM will struggle to process it accurately. How do we establish rigid structure within our text prompts? We leverage XML tags. Using tags like angle bracket context and angle bracket instruction is a heavily recommended best practice, especially for models like Anthropic Claude on Amazon Bedrock. By wrapping your proprietary document in a document tag and your specific question in a query tag, you create explicit mathematical boundaries for the neural network's attention mechanisms. Amazed? The model no longer has to guess where the background information ends and your instructions begin. This is also a critical security practice. By forcing the model to only analyze data within a specific XML tag, you drastically reduce the risk of prompt injection, where a malicious user tries to sneak dangerous instructions into the input data payload. Excitedly, structured, tagged prompts are processed faster, yield much higher accuracy, and represent the absolute gold standard for enterprise prompt engineering. This flowchart demonstrates structural parsing. Wrapping components in XML tags creates a clear boundary between static data and the active query, ensuring optimized model attention and preventing cognitive confusion during generation. Let us bring all these core elements together and see how they're actually formulated in a production Python script. When invoking highly capable models like Anthropic Claude 3 Sonnet via the Amazon Bedrock API, we utilize the Messages API schema. How does this schema support our prompt engineering elements? It separates the system prompt from the user messages array. We define a role and persona inside the dedicated system parameter. Then we construct our specific instructions, XML tagged context, and output indicators inside the user content block.
This programmatic separation mathematically enforces the hierarchy of instructions, ensuring the model never disobeys the system-level persona. Amazing. Let us examine the precise Bodo3 payload structure required to execute this beautifully engineered request. Let's analyze this impeccably engineered API request. We instantiate our Bedrock runtime client. Then we define the system prompt variable. Notice the explicit persona and output constraints. You are an elite SQL admin. Only output raw SQL. No explanations. Next, we craft the user prompt. We use strict XML tags. We wrap the database architecture inside a schema tag, providing the vital context. We wrap our explicit task inside an instruction tag. Amazing. There is absolutely zero ambiguity here. We package this into our JSON payload, mapping the system string to the system key and the user prompt into the messages array. We cap our max tokens to 500 to constrain costs. When we invoke Claude 3 Sonnet, it processes this highly structured, role-driven, context-rich prompt and returns a perfect application-ready SQL query without a single word of unwanted chatty text. This is engineering perfection. This programmatic flow is elegant. The system key enforces the global persona, while the user key provides the XML-tagged context and task. The messages API securely binds them, driving the Claude engine to produce the exact raw output requested.
Our final elements of an effective request deal with refinement and constraints. Sometimes telling the model what to do is not enough. You must explicitly tell it what not to do. This is called a negative prompt. Why is this necessary? Generative models want to be helpful. If you ask for a summary, it might summarize it, but then add unsolicited advice at the end. By adding a negative constraint, like do not include external information or do not use complex jargon, you mathematically steer the model away from unwanted cognitive pathways. It acts as an invisible fence around your output. However, engineering the perfect prompt is rarely achieved on the first try. It requires iterative refinement. You must execute your prompt, analyze the output using the Rakaka framework, checking for relevance, accuracy, completeness, clarity, coherence, and appropriateness, and ruthlessly edit your instructions to patch any failures. Utilize the Amazon Bedrock chat playground to rapidly test and iterate your variables before locking the prompt into your production code. I hope this masterclass in prompt engineering transforms your cloud architecture. We invite you to like, subscribe, and visit quicktechie.com for premium and for recently updated material as per latest syllabus and certification prep, including Q&A banks, ebooks, audiobooks, full training, and interview guides. Behold the life cycle of prompt perfection. We draft a prompt and test the output. If it fails the rigorous Rakaka evaluation, we apply negative constraints and refine. We loop this until it passes, and only then do we deploy to production.